promised, I'm going to walk through portions of the Unit 14 review on Acellus. This is our trig section, and I'm specifically going to cover looking at the Pythagorean identity in more depth, and then also looking at how to determine which of the 6 trigonometric functions to use when solving for a problem. So when I'm looking at the review, one of the first questions that comes up is to select the correct description, right? So you're given a 3-sided triangle, obviously. All triangles are 3-sided. And they're telling you that the side lengths are 8, 16, and 17. And they want you to determine, is it right, is it obtuse, or is it acute? For me personally, when I'm doing these problems, it helps to sketch out a little picture of the triangle. The longest side of the triangle is always going to be the hypotenuse, okay? So I'm just going to draw it under the assumption that it's actually a right triangle because I'm trying to prove whether it is or not. So that's got to be 17, and then this side here would be 16 and 8, right? It looks a little bit more proportional that way. And this is just your reminder that you're supposed to be using either Desmos.com or the Desmos app on your phone for calculations, one or the other, whichever one you prefer. I'll write that down here again, Desmos.com. Okay, so when I look at this problem, if I want to prove it's right, obtuse, or acute, I need to plug it into the Pythagorean theorem. And I know that 17 has to be c squared, because that's always the longest side of the triangle, and then 16 squared plus 8 squared, right? So then you're going to end up with 64 plus 16 squared is all equal to 17 squared, excuse me, which is equal to 289. And then you just add the right-hand side together. So 64 plus 256 is 320. 320 does not equal 289, so this automatically cannot be a right triangle. If this was going to create a right triangle, then these two sides should be equal, so I can cross right off my list. And then the classification of a triangle says that if the left-hand side, or if the two legs are greater, so if a squared plus b squared is greater than c squared, then the angle is acute. If the opposite is true, a squared plus b squared ends up being less than c squared, then it would be obtuse. So since that left-hand side is greater than, acute would be your correct answer for that problem. Okay, let's move into the next type or example of a problem. These aren't actually going to be in correct numerical order because obviously everybody's review will look a little bit different, but I'm going to just kind of use that as a way to show you I'm moving on to another problem. Another sample problem on here is to find the indicated side of the right triangle. So they're already telling you it is in fact a right triangle, which means everything we know about our trig functions is eligible to be used here. So this question looks like x is equal to what? And it gives you this known side is 3. This is 60 degrees. The hypotenuse is x, and that's 30 degrees. So one of the most common questions I've been getting in tutoring when I've been doing these problems is, well, how do I know which function to use? How do I know whether it's sine, cosine, tangent, or what have you? So going back to looking at those notes that we did a couple of days ago, you need to look at what you know and what you need to find. So if it's given that this angle is 30, you know the angle across, which is going to be the opposite of that 30-degree angle, but you don't know the hypotenuse. So you know the opposite, you're trying to find the hypotenuse. So in order to figure out which function to use, you need to take what you know and what you don't know. You know the opposite, you don't know the hypotenuse. So I'm going to use the sine function to solve for this one. And sine is equal, so it's going to be the sine of 30 degrees, which is going to be equal to the hypotenuse, the opposite over the hypotenuse, which means it's going to be the sine of 30 degrees is going to be equal to 3 over x. And now to get rid of that fraction, that x, you need to multiply the x out on both sides. Okay. So I'm going to multiply x here and x here. These two x's cancel out, and I am left with x times sine of 30 degrees is equal to 3. I'm going to divide both sides by sine of 30. Both sides by sine of 30, because then these two cancel out, and all that leaves me with on that left-hand side is x. And then that x, or that 3 divided by sine of 30 degrees, I'm just going to enter exactly that into my calculator on Desmos. So I'm going to do 3 divided by, and I'm going to change my functions here. Click sine and 30. And I can see that that comes up as a -3, which we know is not actually possible when you're dealing with the side length. Clearly, that's not negative. So if you come up with a funky thing like that, then that tells you that your calculator is not in the right mode. I need this calculator to actually be in scientific calculator mode. So let me go back here. See how when I clicked my little wrench up here, it's already automatically on radians. You need to change that to degrees. When I change that to degrees, I get that 3 divided by sine of 30 is 6. And that is my final answer for this problem. X is equal to 6. Okay. Let's look at another problem similar to that. Okay. This one wants me to also find x, and it's another right triangle. This one here gives me that this is a right angle. This is 45 degrees. This is y, 6, and x. So in order to figure out which formula I'm going to use, once again, I need to look at what I know and what I don't know. So this one's asking you to find x. Right next to that 45-degree angle is x. And when it's immediately next to, we call that the adjacent side. And I know the opposite side. So I know 6, and I need to find x. I know the opposite. I need to find the adjacent. I come back and I look here, and tangent is the formula I can use to find opposite and adjacent. So in order to find the tangent of that 45-degree angle, I need to take what I do know. The opposite is 6. The adjacent, I don't know. And then once again, I'm going to do exactly like we did on the last problem. Multiply that x out on both sides. I get that x times the tangent of 45 degrees is equal to 6. I'm going to divide both sides by tangent of 45. These two cancel out, leaving me with just that x. And then in my calculator, once again, I'm going to do 6 divided by the tangent of 45. 6 divided by the function tangent of 45 degrees. And that one ends up being 6 too. They're making this too easy on us there. So I don't know if I can scroll in there. That one also ends up being 6. And then that's going to be my final answer on that problem. Okay, so these are 2 examples of finding the side length when the angle is given. we do need to look at a problem where the angle is not known, but the side lengths are. So I'm going to use another example. This is also from the unit review. This one also says find x, but it says find x degrees. Okay? Focus the camera there. There we go. So in this triangle that's given, we don't know the degrees, but we do know both side lengths. So this is also why 90 degrees down here, x is the unknown angle, and 10 centimeters. So on your calculator, this one looks a little bit different. You're trying to find the degree measurement there. The setup and the function, discovering which function to use is the same thing. So we're trying to find angle x, and we know the opposite and the adjacent. So I can see what's opposite that angle, and I can see what's adjacent that angle. Opposite and adjacent is going to be tangent. Here's the key difference, though. We don't know what the tangent is. So we're going to call that angle that we don't know, x. So the tangent of x is equal to the opposite, 8, over the adjacent, 10. So now how do you do this in your calculator? You don't have to multiply anything out. You actually just need to do the inverse operation. So when I come to functions, I'm going to click function, and I want this tan sub 1. That means the inverse of tangent is equal to 8 over 10, and I'm literally just going to hit the inverse of tangent, 8 divided by 10, and that's going to give me, I'm just playing with the parentheses here for no apparent reason. There we go. That gives me about 38.65, 38.659, but the text, or the, Acellus wants you to round that up. So that 5 would round up that 6, which means we're going with 38.7 degrees there. Okay. And then the last area that I kind of want to recap is that Pythagorean identity problems that I had not taught on notes. So we need to look at them really quickly together. So the Pythagorean identity states that if we're looking at, for example, a circle, right? I'm trying to get it centered there. Whoa, that was definitely not what I was going for. But this doesn't want to spin either. That'll have to work. It's not a perfect circle, but it'll have to work. So it's saying, look, if we have quadrants going through any circle, and we call this the unit circle, and the distance from here to here is 1, and the distance from here to here is 1, this is called the unit circle. So this point would be the equivalent of 1, 0, and this point up here would be the equivalent of 0, 1. So if you were to draw a right triangle at any point of this unit circle, then the hypotenuse or the radius, any of those radii on that circle would also be 1, because every radius or radii has to have the same length, right? So when we look at the Pythagorean identity, that looks like the sine of x squared plus the cosine of x also squared, it's all equal to 1 squared, because we're looking at this side being the sine, and then the opposite side, I apologize, let me reword that. If we're looking at this angle down here, the adjacent side is cosine, and the opposite side is sine. So if you square cosine of x, and you square sine of x, and you square 1, then you would be able to prove all sides of this triangle based on the Pythagorean theorem, right? A squared plus B squared is equal to C squared, and that's true for every single right triangle. So if this is cosine squared plus sine squared plus 1 squared, then it just proves the Pythagorean theorem. So you can use this to solve unknowns of triangles as well. We, however, write this out without the 1 squared because 1 squared is just 1 anyway. So this is the Pythagorean identity that is used commonly throughout Acellus. So let's look at a couple of those problems really quick. Oops. I lost the review. I've got to go back to it real quick. So if we look at one of the problems that is given as an example here, is if we know that cosine of this angle is equal to 4 times the square root of 2 divided by 7, then it wants you to find sine. Okay? When we go to solve this, I rewrite the equation every time. I find it very helpful. I'm going to take sine of x squared plus cosine of x squared is equal to 1. I'm trying to find sine of x squared. So you need to subtract cosine of x squared from both sides. These two cancel out, and then I'm left with just the sine of x squared is equal to 1 minus cosine x squared. Now, we just said that cosine of x is equal to 4 root 2 divided by 7. So I can plug 4 root 2 divided by 7 into what I know about cosine. And that's what this looks like. 4 times root 2 divided by 7, still squared. And whenever you're squaring a fraction, you treat the top and the bottom as separate problems. So you actually are squaring 4, and you're squaring root 2, and you're squaring 7. That's what this kind of breaks down and looks like when you do it. 4 squared, don't forget we still have our 1. 4 squared is 16. Whenever you square a square root, it just drops the radical. It just takes the whole number underneath the radical. So root 2 squared is just 2. And then 7 squared is obviously 49. 16 times 2 is 32 over 49. Well, now I've got 1 minus 32 over 49. That's a bit of a mess. But wouldn't you agree if I told you that 49 over 49 just equals 1? 49 over 49 minus 32 over 49 is a much cleaner problem. And don't forget to bring this guy down. We're still solving for sine of x squared. So sine of x squared is now equal to 49 minus 32 is 17 over 49. But we're not trying to solve for sine of x squared. We're trying to solve for sine. So undo the square root, but whatever you do to one side, you must do to the other. The square root of sine of x squared is just sine of x. The square root of 17 cannot be simplified any further. So we're going to leave that under the radical as the square root of 17. But the square root of 49 can be simplified to 7. That is our final answer. The sine of x is equal to the square root of 17 divided by 7. Okay. I'm going to do one more problem. And let me make this part clear. Whether you're finding sine or cosine, this process is all the same. So if another problem asks you to find cosine, you're just going to subtract sine of x from both sides so that you've got cosine of x squared is equal to 1 minus sine of x. You can manipulate that theorem in either direction, or that identity property in either direction. So last problem real quick. Sine of x squared plus cosine of x squared is equal to 1. What's given in this problem is that the cosine is equal to the square root of 5 divided by 3. You need to find sine. Okay, so once again, I am going to start by rewriting the entire equation. It's all equal to 1. If I'm trying to find sine, then I'm going to subtract cosine so that the equation is rewritten in the form that I'm solving it, right? In the unknown. So sine of x is what is unknown. I want it alone by itself on the left-hand side. And that's all going to be equal to 1 minus cosine of x squared. I know that cosine of x is equal to root 5 over 3 squared. When you multiply or do root 5, that just undoes the radical. And then you multiply or you square 3, and that gives you 9. And keep remembering to bring sine of x down because we have not solved that on the left. I don't know what 1 minus 5 over 9 is, but I know that 1 is equal to 9 over 9, because 9 divided by 9 is 1. Minus 5 over 9 is equal to 4 over 9. Okay, final step. You need to take the square root of both sides. The square root of sine of x is just sine. Sorry, the square root of sine of x squared is just sine of x. The square root of 4 is 2, and the square root of 9 is 3. So that one ends up really pretty without any radicals without any radicals remaining. You're able to find perfect squares in both of those. All right, and that is all for today.